Physics is the study of how matter acts. It encompasses forces, motion, energy, and many other similar topics, electricity, magnetism. It describes the motions of everything from the smallest subatomic particle up to how galaxies interact with each other throughout the universe. So it encompasses and describes everything that the eye can see, even if you have to look at it through a telescope. As we study physics, we use math to describe these actions. Math is the language that physics is spoken in. And if, as you take this course, you realize that you're really weak in algebra and math is not your strong point, I would strongly encourage you to take some extra time to hone your skills and sharpen them up because you're going to need them a lot. In the back of the G.N. Coley text is an appendix that has the basic skills that you'll need in this class, and you can go over it and make sure all of those things make sense to you. As we go through and study physics, there'll be a little bit of reference to the scientific method. As time has progressed, more and more and more information has been added to our body of knowledge. And so what we're going to present is the best picture that we have right now. In many cases, there's a picture that may not be the very best picture, but it's a subset of an accurate description that works very well for everyday life. And you'll be told when that's the case. And the scientific method essentially is what happens to come up with the rules governing science as we know it today. It starts out when someone makes an observation and they try to describe why things are acting the way they act. And so they'll develop a hypothesis. They'll say, well, I think it acts this way because, and they will describe what is happening. And then they'll submit these ideas to the scientific community. And then many people will test them out and see if their research supports the hypothesis. And if that happens time and time again, and these rules are found to work more and more, then many times it will start becoming a theory. It'll be called a theory. And good theories also will predict not only describing the motion that was observed in the first place, but they'll predict what should be observed in other situations. And a really good example of that is when we look at astronomy, at first people didn't realize that the Earth orbited the sun, for example. And so for a long time, people thought the Earth was the center of the universe. Galileo came along and he was able to show and observe the moons of Jupiter and say, look, something is orbiting another celestial body, not just the Earth. And so he added his observations, and over time, it began to be accepted that the Earth was not the center of the universe. And so actually a couple hundred years before Galileo, Copernicus shifted the center from the Earth to the sun, said the sun was the center of the universe, which obviously we know is not true today, but it was more accurate than saying that the Earth was the center of the universe. So over time, men have added more and more knowledge to where we have a more and more accurate understanding of the motions of the heavens. And we had Newton come along and describe universal gravitation. Everything acts the way it does because of the force of gravity. And that described nearly all of the motions that people saw, and not quite all. And so then when Einstein came along with general relativity, that described motions of still more of the universe. And he said, if my hypothesis is correct, not only is it going to describe how some of these things interact with each other, but it's also going to show light bending toward a more massive object. So he made a prediction, said this will be seen. And then during an eclipse, that was actually shown to be the case. And so what we have today is we have the information that has been gathered over centuries adding together to give us the most accurate picture. And so that's how the scientific method works. It's a lot of observations. Things are submitted to the scientific community. You've got peer review going on and checking to see if these things are accurate. And what I would love for you to do is, as you have information come your way, be it Facebook or wherever, submit a little scientific thought to it. Is this somebody's blog site? Is it their opinion? Or has this information been submitted to the scientific community and shown to be accurate? And so we should end up with a better and better picture of how things work. And interestingly, in science, we don't have an absolute answer for everything, because if an observation is made that seems to contradict the body of knowledge that we understand it, then that body of knowledge needs to be amended and changed a little bit and made more accurate. So anyway, we're not going to talk a lot about the scientific method as we go through that course, but it's part of introducing you to science and how things work, so that we can have the best understanding possible. All right, I want to move into some of the information that you're going to need as we progress through this class. I told you that math is the language of physics, and so we're going to be using a lot of numbers. We're going to be looking at measurements of things. How fast are things going? What position is it in? Is it accelerating? As we record measurements, there is a thing called uncertainty that's associated with every single measurement we take. I have right here a ruler. Hold it up so you can see that it's got centimeters marked. It's got inches. The inches are upside down. And within those centimeters, it's got the millimeter markings as well. And so if we take a measurement, we could measure something to the nearest millimeter. We could maybe even estimate where in between the millimeter marks something landed. But beyond that, we could not take accurate measurements. Every single measurement that we're given has some associated uncertainty with it. We can have more and more precise measurement instruments, but at a point, we can't have a perfect precision. That will never happen. And so there is uncertainty associated with every single number that we take. So for example, if I measure the width of this paper, which I have, and I use the millimeter markings, my measurement, it could be maybe not lined up quite right with the ruler on either end. I do the best that I can, but I'd realize that my readings will probably be accurate to within a millimeter. I could say that the width of this paper might be 21.6 centimeters, because the tenths of centimeters are the millimeter markings, and I would estimate that I could be off by as much as a tenth of a centimeter. Okay, and so the uncertainty, this would be the uncertainty of that. And if I wanted to find the percent uncertainty that that was off, I would take that 0.1 centimeter divided by the 21.6 that I measured, and then you'd multiply by 100%, and I would get that that would be about 0.5% off. So we've got, again, it's times 100% to get a percent out of there. And so that would be the uncertainty that would be associated with measuring something with this ruler. All right. And in this class, in the lecture portion, we're not going to be dealing with uncertainty a whole lot. We'll save that for the lab. But I want you to be aware that it exists. And the way that we're going to acknowledge uncertainty in the lecture portion of the class is by paying attention to how we state an answer. And so we're going to be using something called significant figures. Significant figures, abbreviated as sig figs, because it's much easier to say and it gets brought up a lot. The number of significant figures indicates the reliability of our number. It tells us how accurate we can expect our number to be. With my example earlier on measuring the width of this page, the width of that page was 21.6 centimeters. Okay, this is a 3 sig fig number. This is saying I know the reliability of this number to within a tenth of a centimeter. Okay, and I could not say, if I said 21.60, I would be indicating that I knew the accuracy of the width of this paper to 100th of a centimeter, which I do not. All right, and so this would indicate a fourth significant figure. Interestingly, when zeros are placed at the end, like if I had 2100 millimeters, okay, this would only have two significant figures. I'd be saying I have 2100 millimeters. It could be, 20 50, it could be 2150. It's somewhere in that range. The zeros simply act as placeholders. Okay, and the only way we can know whether zeros are acting as placeholders or not is by writing the things in scientific notation. And I'll get onto scientific notation here in just a moment. Okay, also I want to spend a little bit more time on significant figures. And so there are some rules governing how we state our answers, because many times you'll go through a mathematical operation and multiply numbers or divide or something like that to get to the final answer. And so I'm going to show you an example of finding the area of this page, of my page of notes. And so the width is 21.6 centimeters. When I measured the height of the page, I found that it was 27.87 centimeters. Okay. And so to find the area, I multiply these two values together. And when I did that, I got 600.48 centimeters squared. Okay, from multiplying these two values together. And so this answer right here implies, if we talk about significant figures and how accurately we know the answer, this implies that we know that to 100th of a square centimeter. That doesn't make sense. We only know the lengths of the sides to within 1/10 of a centimeter. So the rule for sig figs that I'm going to want you to follow when you write down the answers is to see how many sig figs are in each of your values. The one with the smallest value is how you're going to round your final number. In this case, each of these is 3 significant figures. And so this answer would round to 600 centimeters squared. Okay. And it's a little bit interesting with square centimeters when we say 600. First of all, that could be one sig fig. We could be saying, well, it could be between 550 and 650. It's around 600 square centimeters. Okay, this is really an ambiguous way to state the number. And so if you've got a value like that, I would encourage you to use scientific notation. So that's another thing that you're going to be needing to use, scientific notation. Okay, so when you're going to write something in scientific notation, the approach that you take is to take the number that you've got, the 600, and write it as a number between 1 and 10. So you put the decimal wherever you need to put it to turn that into a number between 1 and 10. In this case, it's 6. We're either going to say 6.00 because these are significant figures. They indicate a level of accuracy that just 6 by itself would not. So we've turned this into a number between 1 and 10. And then the next thing we do is we multiply that by whatever power of 10 it takes to get it back to the original number. In this case, you'd have to multiply it by 100, or 10 to the second. Okay, so this is written in scientific notation. Again, the number is a number. You write it as a number between 1 and 10, and then you write your multiplier to get it to whatever number it's supposed to be. Okay, so then I could look at this number and say, oh, yep, this is a 3 sig fig number. That is what it should be for this particular answer right here. So as you go through this class, I expect you, when you give an answer, do not write down every single digit that the calculator tells you. That's what you do in math class a lot. This isn't math class, this is physics. And these numbers actually mean something. The number that you put down indicates how the level of accuracy of your measurement. Okay, and if you're only accurate to 1/10 of a unit, then you better make sure that your number reflects that. All right, so significant figures are pretty important. If you've had chemistry class, likely you have gotten good at significant figures, and if you haven't, you can become good in this class. So take care to pay attention to the significant figures. It's an easy way to lose a part of a credit for homework problems and stuff like that if you don't pay attention to significant figures. Another thing that's really important that you pay attention to is units. Alrighty, and so you may have noticed when I multiplied these two values together, I multiplied the numbers and got a number for how many square centimeters I had. I also multiplied the units, so these units, instead of being centimeters, are centimeters squared. That's super important. A centimeter is a unit of length. Okay, this would be a centimeter. A square centimeter is how many little squares this size are in whatever it is we're talking about. There's a world of difference between a centimeter and a square centimeter. And also different is a cubic centimeter. Okay? You can't write this down and say centimeters and get all the points, okay? Units are important. Units are incredibly important. Without units, the value that you put down is absolutely meaningless, unless it's just some sort of a ratio that doesn't have a unit. That happens once in a while, but nearly everything should have a unit attached. So it's super, super important. Your answer is not correct without units. If you were to tell your friend, I hiked 10, that would not convey really any information whatsoever. You could have hiked 10 inches or you could have hiked 10 miles, okay? Without units, you're not really saying much of anything. So units are very, very important, alrighty? And so make sure as you go through and complete homework assignments, you've got units attached to everything. We're going to be using SI units as we go through this. Okay. SI is an abbreviation for French words that mean the International System of Units. System International. Okay. And the SI units have as their base units the meter, the kilogram, and the second. Okay. This right here is not an SI units. Many times, honestly, as you're going through and completing a homework assignment, I don't necessarily need it to be in SI units. All right. You are going to want to get into the habit of converting it into SI units because we're not just going to have meters, kilograms, and seconds. We're going to have combinations of those units for the answers to many things. And if you get everything into SI units, you're probably not going to mess things up. So it's important that you convert into SI units. And it's interesting, these SI units have standards that define how large they are. The meter is defined in terms of the speed of light. Okay. For a long time, they had a bar made of a platinum iridium alloy that had marks between it indicating what a meter was. Unfortunately, they made several of these and had them in various places around the world. And then when they got them all together, just the conditions they were stored in and things like that, they weren't exactly on. I don't think they were off enough that any of us could have figured that out. But when you have a unit of standard, you need it to not change. All right. And so the unit of the meter was then redefined in terms of the speed of light, which is a constant, the speed of light in vacuum. All right. The second used to be defined in terms of a day. It was one small portion of a day, 1/86,400th of a day to be precise. And now it's defined in terms of the rate of radiation of a cesium atom. All right. And so as accurate as a day is, this is even more accurate. So we have a constant in nature that we can take and be seconds. Kilograms, interestingly, was defined as the weight of a liter of water. A liter is 10 centimeters square. It's a 10 centimeters square. So you've got 10 centimeters on each side. Okay. And a liter of water weighs right about a kilogram. And they've got a mass of, again, platinum iridium that is kept near Paris, France. That is the standard kilogram. And I believe they've also found a constant in nature in which they define the kilogram as a certain standard. But anyway, that's roughly what a kilogram is as far as what you tie it to see how much it is. So those are the SI units that you're going to be finding things in terms of. And then we have a bunch of metric prefixes that we'll put before these different units to indicate either more or less of them without having to say, instead of saying 1,000 meters, we can say a kilometer, okay? Instead of saying 1,000th of a kilogram, we can say, well, a gram, of course. K is kilo. This is 1,000 grams. That metric unit is already there, okay? And we can put other things, other terms in front of them, okay? We can have a megameter, 10 to the 6, 1,000 or a million meters, alrighty? And so the metric prefixes, I'm going to want you don't have to memorize every single one of them. There's a table in the book. I don't have them all memorized. I never use them, okay? They are there and it would be good to consult with them. The ones I do expect you to know, I expect you to know that K is kilo, okay, and it means 1,000. So you can have 1,000 seconds as well, a kilosecond, alrighty? And mega is represented with a capital M, mega, and it means 10 to the 6th, okay, or a million. Giga is 10 to the 9th, okay. Again, you could have a gigameter or a gigagram, okay, 10 to the 9th grams. So all of these things could be put in there. And then I'll also write a few more over here. I want you to memorize that a lowercase c is centa, and that's 1/100th. Okay, a centimeter is 1/100th of a meter. All right. And if you think of that terms centa, century is 100 years. Okay, a cent is 100th of a dollar. And so you have things in everyday life that you can compare this to. So if you're not entirely sure, think of that, because people have a tendency to mix up C and then M is milli, and that's 1,000th of a unit, a millimeter. Okay, a millennium is 1,000 years, 1,000th. And again, people have a tendency to mix these up a lot because we use centimeters a lot when taking measure, and then we'll use millimeters, okay? And so if you ask on a test, oh, by the way, is this 100 or 1,000? I expect you to remember, okay? So don't ask, just memorize them. Okay, this little symbol here is a Greek letter mu, and it means micro, and that's 10 to the -6th. A micrometer. Another standard thing that people mess up is they will use an M for a micrometer when M means millimeter. There's a 10 to the 3rd difference between the two. Don't mess that up. Micro is 10 to the -6. M milli is 10 to the -3. It's 1,000th. Okay, and another thing that I want you to remember is that N is nano, and that's 10 to the -9th. And you're not going to be needing that much until we get into the wavelengths of light, but I do want you to have this memorized so that when the time comes, you will automatically know how to convert them into meters. So that's what I want you to know as far as metric prefixes go and how to use them. SI units, okay? Writing things in scientific notation and making sure you have the appropriate number of significant figures is really important as well. And I'll cover a few more introductory ideas on the next video.